Hey everyone, we're so used to thinking about data as pairs, right? One friend connected to another, one city linked to the next. But what if the real story, the most important stuff, is hidden in the groups? Today, we're going to look beyond the simple link to explore the powerful, hidden shapes within our data. So let's just start with this question. What if the most important stories your data has to tell aren't in those one-to-one connections? What if they're actually revealed in groups of 3 or 4 or even more, all interacting at the exact same time?
To answer that, we first have to talk about the standard way we look at data and, where it kind of falls short. So let's dive into our first section, Beyond Pairs, the graph's limit.
For, decades, the go-to tool for mapping out complex systems has been the graph. The idea is super simple, but really powerful. You have your objects, which we call nodes, and the connections between them, the edges. You know it. It's basically a network of dots and lines.
And don't get me wrong, graphs are incredibly useful, but they have this one fundamental blind spot. They can only see a connection between 2 things at a time. Their entire universe is built on these one-on-one or pairwise relationships.
Let's make this real. Think about a social network. A graph can tell you that Alice is friends with Bob, and Bob is friends with Carol. Easy enough, but it completely misses the most important detail. Are Alice, Bob, and Carol an actual friend group that hangs out together? A graph just sees a chain of links, but topology, that lets us see the whole cohesive group dynamic.
Okay, so if graphs are stuck looking at pairs, how do we start to see these really important group interactions? Well, that brings us to this amazing idea. Data has shapes too.
To really see that bigger picture, we need a totally new language for our data. We've got to stop thinking just in terms of points and lines and start seeing the actual shapes they form. This is the world of what researchers call higher-order structures. Now, the tool that lets us do this is called a simplicial complex. Okay, it sounds complicated, I know, but the idea behind it is actually really elegant. It's just a way of building structures not only with points and lines, but with filled-in triangles, pyramids, and whatever comes next. It's a whole framework designed from the ground up to capture those group interactions that graphs just can't see. Let's just build one really quick. It starts with what we already know. A 0 simplex, that's just a point. A node. A 1 simplex, a line connecting 2 points. An edge. But here it is. This is the game changer. A 2 simplex is a filled triangle. By filling in that space, we're not just connecting the dots, we're officially saying these 3 things form a real group.
I mean, just look at the difference here. A simple graph would only show you the 3 lines, the outer edges of this triangle. But the simplicial complex shows us the filled-in shape. That shaded area isn't just for decoration. It is an explicit signal that a true 3-way interaction is happening. That is the story we were missing before.
So, we can see our data as shapes now. That's cool, but what can we actually do with them? Well, it turns out these shapes unlock this incredibly powerful mathematical toolkit. They give us an entirely new language for data.
The real power here, the secret sauce, comes from a mathematical framework called Hodge theory. Think of it as the engine that lets us analyze these shapes, turning them from just being pictures into deep, actionable insights about how a system works.
So what does Hodge theory actually do for us? Well, its main tool is something called the Hodge decomposition. Imagine you've got some complex signal, like information or energy, flowing all over your network. It's a mess. This method lets you take that messy signal and break it down into 3 fundamental, perfectly separated components. Okay, let's break these down. First, you've got gradient flow. This one's easy. It's a direct, downhill flow, kind of like water running from a high point to a low point. Simple. Second, there's curl flow. This is a local, circulating flow. Picture a tiny whirlpool or an eddy spinning around one of our data triangles. And finally, you have harmonic flow. Now, this one is often the most interesting. It's a persistent, global loop that flows around a major hole or a void in the data. It represents trapped circulating energy that just can't find a way out. And right here, for the first time, we can actually see these flows completely separated. We can pinpoint the direct gradient flows, we can see the little circulating curl flows around those triangles, and we can even spot that one persistent harmonic flow looping around the hole right in the middle. By pulling these apart, we can finally analyze these hidden dynamics that were totally invisible before. So, we can separate these flows. What does that actually let us do in the real world? This is the big payoff. We are now seeing what graphs can't. So really, why does separating these different types of flow actually matter? What real-world problems can we suddenly start solving?
Well, the applications are just incredibly broad. In brain networks, it helps us see complex thoughts that go way beyond one neuron just firing another. In statistical ranking, it can instantly spot impossible loops. Like when a survey says people prefer A over B, B over C, but then somehow C over A. That illogical circle, that's a curl flow. It's also being used to understand the 3D structure of molecules, to better model traffic grids, and to process complex geometric shapes.
The researchers behind this work put it perfectly. They said that when what you're trying to predict depends on these circular flows, graph-based methods inevitably lose valuable information, while topological methods can effectively preserve and capture it. In other words, sometimes the most important part of the story is the exact part the traditional methods were designed to throw away.
And this huge shift in perspective, it really leads us to our final thought for today. The future is topological. By learning to see the hidden shapes in our data, the groups, the loops, the voids, all these complex structures, we're getting a much, much truer picture of the world around us. We're finally moving from a flat 2D map of connections to a rich 3D world of real interaction. And that just leaves us with this one thrilling question. If we've only just learned how to read the shape of our data, what other hidden dimensions, what other secret languages of our world are we about to discover next?